So the geometry of an ellipse, let's start with how we draw an ellipse. If you compare this to the circle, instead of there being one center, there are two centers, and we still have a loop of string, so that the length of this side and this side and this side stays constant. If that's a loop of string, then the lengths of these, as we try to draw a circle or a circular type shape, those lengths, 1, 2, and 3, will change, but the length of the total length will stay the same. So as we move that pencil around, it will trace this circle like so, a circle that has two centers. And so you might also imagine that as we move these two centers closer and closer together, as they get closer and closer together, it gets closer and closer to being a circle. So we might say then that as a circle is an ellipse where the distance between the two centers is 0. So I illustrate that to point out that there is a range of the way ellipses will look, and they can look more and more like a circle or less and less like a circle. And for those that will look less and less like a circle, the distance between these two centers will get farther and farther apart. All right, so we just talked about how to draw an ellipse. The basic attributes are the center. Well, we didn't even really mention a true center. There is a true center of an ellipse. There is a true center. And when these other types of centers, when it's an ellipse, we call those, each one is called a focus. And when there is more than one, if we're referring to both of them, the plural of it is foci. You might hear some people say foci, but that's really not the correct pronunciation. It's foci. So when we decrease the distance, eventually the distance between the foci will become 0 and we have a circle. And as we mentioned in the previous video, we have the major axis, half of which we would refer to as the semi-major. And we also could have our other axis that goes through the center, which we would call the minor, or half of which we would call the semi-minor. And this is where that distinction becomes important, because as you can see, as this thing becomes more and more elliptical, the semi-major, the black, becomes increasingly longer compared to the semi-minor. You might also notice that if the semi-major axis is this whole length, and the semi-major is half the length, and minor is the entire, and the semi-minor is half, it really doesn't make a difference whether we're talking about the major or the minor, because they compare to each other the same way. Let's illustrate what I mean. If the major axis is, let's say it's 10 units long, then that means the semi-major is 5. And if the minor is 6, then the semi-minor is 3. So if we compared, let's say, the major to the minor, that's 10 to 6. If we reduce that, since they're both even numbers, we could reduce that to 5 over 3. Now notice then, that's the same ratio as the minor, or as the semi-major to the semi-minor. So let's see here. Now looking more largely at our drawing, we have our minor axis and our semi-minor, exactly twice as long, and our major and our semi-major. Our two foci, here's one focus, here's the other focus, and there's the actual center. Now, what we call this point out here on the semi-major axis, way out on the end, we call it a vertex. And we call the other side a vertex. And when it comes to the minor axis, we call this a covertex, and this one a covertex. So we can refer to the vertex, or the vertices, plural, the covertex, or the covertices, the plural. And so this is the geometry of an ellipse. Again, going back to our definition of what Kepler's first law is, Kepler's first law says a planet's orbit is an ellipse with the sun at one focus. So if the Earth were a pale blue dot, it would reside out here like so. Now, this ellipse is extremely exaggerated from its true scale. If you were far enough to see the sun in its Earth's orbit from this far away, like we're looking at this page, it would look very much like a circle, but it is not a perfect circle. In fact, this Earth's orbit is so close to being a perfect circle that if the sun were in the center, both foci reside inside the sun. So again, the distance is very small compared to the size of the orbit. But the orbit is an ellipse nonetheless. So this is the idea of what we have as the orbit of Kepler's first law. And this is true of all objects that have orbits. We could change our perspective and say, wait a minute, this is the Earth, and this is the Moon in its orbit. And the Moon in its orbit around the Earth has an elliptical orbit. Again, it's not as exaggerated as this. The word for exaggerated or difference from a circle is the eccentricity. And that is given as the letter E. And that eccentricity is how much an orbit deviates from a circle. So if it is a circle, for a circle, the eccentricity is 0. So the larger a number is, the more eccentric or different from the normal it is. And that's our treatment of Kepler's first law.